Dr. Preeti, are we ready for the second session? Preeti ma'am, welcome back. Are we ready for session 2?
Yes.
Yes, ma'am. Please go ahead.
All right. So what we will do now is that yes. So we'll first do the last bit of what we were talking about, fixed effect model, and then I will summarize it again, whatever we have done until now related to fixed effect model, and then we will start with the random effects model. All right. So let me complete the last bit, which where we left in our last session is assumptions of fixed effect model. All right. Now here we know that what our model is. We have YIT is equal to beta 1 XIT plus dot 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 beta K XIT plus alpha I or AI plus our error term. All right. Now, the common assumption is that first thing is, of course, we know that the sample that is drawn is a random sample. So, or each and every cross section has been, or the entity has been selected or chosen randomly. All right. And we also know that the other thing is that the explanatory variables are changing over time. And also the other thing is that there is no linear relationship amongst the explanatory variables. All right. Now, the next thing is, so what we are doing, number one is, the assumption number one is that each entity has been selected randomly. So each cross section is a random sample. Okay. Second is that the each explanatory variable is changing over time, and also that these xi's are not linearly correlated. All right. Then third is that we know that for each time period t, the expected as the same explanations, the assumptions are going to be the same, which we have already discussed. I'm just writing here so that you should keep that in mind. So expected value of the error term conditional upon the xi's and the ai is equal to 0. You know what this means. All right. Then the other assumption is that the variance of error term conditional upon the xi's and the ai's is variance mu by t, which is constant. Okay. Then is next, or the last, is that for all values where t is not equal to s, the covariance between mu I t and mu I s conditional upon all xi's and ai's is equal to 0. All right. Now, the condition that the explanatory variables and the intercept terms and the error terms, they are independent and identically distributed as normal distribution with mean 0 and sigma mu square as the variance. All right, or standard deviation is sigma mu. So these are the assumptions of fixed effect model. Now, so how do we decide that whether we should, okay, now what I will do, before we start with the random effect model, I would like to summarize what we have already done so that you can easily understand that where we are going. All right. So you remember what we started with, okay? What we did was we discussed one thing. First, we discussed that what is cross-section data. Then we discussed what is time series. We did not explain it, but we just kind of said that, okay, there is cross-section data, there is time series data, and then there is pooled cross-section data, and then there is panel data. All right. Then what we also did was that depending on seeing that in our equation yit is equal to alpha plus alpha plus beta xid plus error term. In this, we have seen that if our alpha is assumed to be constant, then we are going to do the pooled OLS. All right. And if it is different, then we were going to use either the fixed effect model or the random effect model. All right. Now, what we have already done is we have seen in case of fixed effect model, what are the things that we have done is number one that we did was what is also known as the within group. All right. So in case of within group fixed effect model, what we did was basically we estimated OLS from, you remember, that is from the demeaned values. Okay. So, and what we were seeing there was we were seeing the deviation from the mean of the variable. Right? We did that.
Ma'am, in
Then,
deemed value,
demeaned
equation, you haven't tried the alpha value. Why so? Can you explain me, ma'am?
Yeah, because in that case, what we are doing is we are already transforming. So, and that you saw that equation in that what we did, we were doing the averaging, right? And
Yes.
when we were doing the averaging, we were doing it for that particular variable where the values were varying with respect to time.
Yes, ma'am.
Right? Right?
Yes, ma'am.
Whereas in case of alpha, we don't have the subscript t.
Yes, ma'am.
So that means it is not varying with time.
Yes, ma'am.
So alpha minus alpha will be equal to 0. I mean alpha
Okay.
I minus alpha I.
Okay, okay, ma'am. Okay, thank you. Yes.
Yeah. What we did was first we have discussed about the within group estimation, and where we did the did the estimation of demeaned values, and we saw the deviation from the mean value of the variable. All right. Then the other method that we also use is the way we have done this, in the same way, we have another way to do, and that is known as first difference fixed effect model. So yeah, there is not much difference between this and this. The difference here is in case of within group or in case of demeaned values, or where we saw the deviation from mean of the variable. In case of first difference, what we do is the methodology is exactly the same, estimation is same, but we do the estimated OLS where we see the deviation from the successive values of the variable. All right. So do you understand this? So in case of within group estimation, what we did, we had our YIT, right? What did we do? What did we estimate? YIT minus Y bar I, right, is equal to, right? This was our method. This is how we estimate the within group fixed effect model. In case of first difference, what are we going to do? In case of first difference, we are going to do the deviation from successive values of the variable. All right. So what we would do basically is we will have y. Suppose we are having here y1 y1 for time period. Suppose that it is t1. Okay. Y1, sorry, not one here. yi t1, all right, minus yi d2. All right. So we are here. What did we do? We did the deviation. We were estimating deviation from the mean of that variable, which is here in this estimation here we are having. This is the mean, right? In case of first differencing, what we are going to do is we are going to do the deviation from the successive value. Is that clear? So this is also a kind of fixed effect estimation. Now, one thing that we did not do in detail, which I should have done earlier itself, that is, I did mention it, but I think I did not explain it. That is the least square dummy variable method. Now, in that, what we do? In least square dummy variable method, we know that in our equation, YIT is equal to alpha plus beta 1x. Now, what we are doing here is that in case of least square dummy variable, for each entity, all right, that is case. For each case, and case is represented by I, okay. For each case, we create a dummy, all right. Now, only thing that we need to remember here is that when we are creating the dummies, right? When we are creating the dummies, the number of dummies will be one less than the number of cases, which is corresponding, which is represented by I. Okay. So, for example, if in your analysis, if suppose in our last example, when we were saying we had Uttar Pradesh, we were talking about Madhya Pradesh as one entity, Uttar Pradesh as another entity, and Orissa as third entity. So there are three entities there. Now when there are three entities there, what we would do is we would basically create two dummies. All right. Now those two dummies, what those two dummies would be representing? For example, we create dummies. We have states, we have Madhya Pradesh, Uttar Pradesh, and Orissa. And we create dummy for Uttar Pradesh and we call it as D1, or if you don't want to get confused, you create it as D2, okay? And for Orissa, D3. Why I'm keeping 2 and 3 here is because this is our case or identity number is 2. So this I here is equal to 2 and I here is equal to 3. And that is why conventionally I'm keeping this dummy value as D2 and D3. And I will not create any dummy for the first case. That is I is equal to 1 for Madhya Pradesh. Why? What is going to happen is that in this example, suppose that in this example, we see that if we were to apply the dummies there, then beta 1x plus beta 2 d2 plus beta 3 d3 plus mu it. All right. Now here, what is going to happen is that this dummies, in fact, although here I'm writing this as B2, but to not get confused, the interpretation of slope for a dummy variable is not done in the same way as it is done for the slope of the explanatory variable. Hence, oftentimes it is also written as delta 1. Sorry, not delta 1 here. It will be delta 2. And this slope can be written as delta 3. Now, what does D2 represent? D2 will assume values 0 and 1. Now, that what it would mean is that in your matrix, what you're going to have is that for all the for entire column of D2, everywhere it will be 0 except for the case which is I is equal to 2, which is Uttar Pradesh in our analysis. So there we will have it as 1. So that means that data is for Uttar Pradesh. So whenever we are writing, we are going to choose value 1 wherever the whatever concept we are dealing with is present. So when it is present, we write 1. When it is not present, we write 0. So in this case, Uttar Pradesh, wherever Uttar Pradesh is present, we will write 1. And for the rest of the column, we will enter 0. Similarly, for Orissa, we will have D3, wherever Orissa is coming, there will be 1. And wherever it is not appearing, it will be 0. Now, why we did not take dummy for Madhya Pradesh is, one thing is that the estimation of these dummies is going to give us the value of intercept, the values of estimators for these dummies, and the one which is left will be kind of approximately be taken care by the alpha. And another reason is that when you are going to, if you are going to put D1 also as a dummy in your data, then there will be at least that one case where there will be complete linear relationship. All right, that is why we will not be able to run the analysis. So in case of another way, the next step relating to this is, in case of least estimation of the impact of the dummies, we can also do one more thing, that if we want, if this introduction to dummies is what is going to help us in kind of bifurcating this term alpha. Okay, because this is not, and here what is going to happen with dummies, will we be able to take do anything which is time variant? Yes or no?
No.
Can you please tell? Someone has already answered. I could not hear properly.
Ma'am, can you repeat the question?
Yeah. So see, the question is that you remember that when we started this entire estimation, our objective was to capture the effects which are either time constant or time variant through this intercept term. All right. So whatever we are doing is we are trying to address it through this intercept term. Now, in case of fixed effect and random effect model, we know that we are not assuming that this alpha is constant. That means it is different. It is different for different entities. All right. Now, when it is different for different entities, in case of estimation, we are doing these three methods. One is within group, second is first difference, and third is the least square dummy variable. Now, when we are doing the estimation by method of least square dummy variable, what we are doing? We are introducing dummies. Now we are introducing dummies, and I have already shared this, that for I, that is the number of i's which are there, the variables, dummy variables will be created for number of i's minus 1, right? So we are, if there are 3 i's or 3 cases, 3 entities, we are creating 2 dummies. All right. Now, in this analysis here itself, now we have introduced these 2 dummies and their coefficients, their estimators, instead of beta are often also written as deltas, so that we can easily distinguish those from from the coefficients which are for explanatory variables, because their interpretation is done differently. Now, can you please tell me that will these deltas have any impact of time? Will those be time variant? Will there be any role for time, or yes or no?
Yes, ma'am. I believe yes. Time will be involved
Why time will be involved?
because in the panel data we are the variables which are we are considering is related to time. There is a big data.
Okay. See, the panel
Time
data
dummies.
and panel data has the component of time, but these dummies are for the specific entity. Okay.
Yes, ma'am. Yes, ma'am.
So if suppose you were to, when you see this data, how will your data look like? You will have your Y here, you will have your X here, you will have your dummy 2 and dummy 3. All right.
Yes, ma'am.
Basically,
Yes, ma'am.
you will also have dummy 1, but that you are not going to include in the estimation.
Model.
Yeah. So for dummy 2, it is for. Now, when you are entering the data, first you are entering the data for Madhya Pradesh, then you are entering the data for Uttar Pradesh, then you are entering the data for Orissa. So you are
Ma'am, this is state-wise yearly data or just for a state only?
No, we are talking of panel data. So this Madhya Pradesh
Time
here
will
is your
considered.
2000, yeah, 2001, 2002, 2003, 2001,
Definitely.
2002, 2003.
Yes, ma'am.
2001, 2002, 2003. But when you are entering the data here, these xi's will be different, yi's will be different, because those are having both the components I and T.
Yes, ma'am.
But what does the dummy represent? Dummy represents only the entity. That is the case. So which is not varying with time. So in case of our first D1, we will have 1 here, 1,
Yes,
1.
ma'am.
And here we will have 0, 0, 0. In case of D2, we'll have 0, 0, 0. Uttar Pradesh 1, 1, 1. And 0, 0, 0.
0, 0.
And here it will be 0, 0. And here it will be 1, 1. So what is happening? This is not time varying. So that is why you will not have a component of time. Okay.
Now it's clear, ma'am. Thank you so much.
Yeah. So now,
Ma'am, when we are not taking dummy for Madhya Pradesh, so why we have written D1 there?
no, that is, I am saying just so that this, we will not include this.
Okay.
This
okay,
column will not be there. This is,
Okay.
I am for simplification only I am saying this.
Okay, ma'am. Okay.
Yeah.
But can you explain once more why you are not considering in Madhya Pradesh?
Yeah, because see, when you are going to estimate this, or when you are going to run this model, what you will have, if suppose I include here dummy 1, which is for Madhya Pradesh, then that will have a dummy 1, then what is going to happen?
Then UP is dummy.
Error time will be high.
No. There were two things which I explained. Okay. Number one is that when we are estimating this model, so this estimator is going to tell us that what is the impact of this particular state, which is Uttar Pradesh. Okay. And this is beta 3, or basically delta 3, with respect to the dummy variable 3, is going to tell us the estimation, or which will be the coefficient for the state Orissa. All right. Now, we are still continuing with this term, which is alpha. So more or less, it is not 100%, but more or less, the remaining time constant effect will be taken care by this alpha, which is for Madhya Pradesh now, because it is the remaining part. See, this coefficient is going to tell us about Uttar Pradesh. This coefficient is going to tell us about Madhya Pradesh. So, and alpha is still there. So alpha is going to take care of the first component, that is Madhya Pradesh. Is that clear?
Ma'am? Yes. But ma'am, beta 1x is explain the
Beta 1x, this is the explanatory variable. These are the dummy variables. This x is explanatory.
Independent.
Yeah, independent.
Ma'am,
Yes, please.
ma'am, if we create dummy variables for all three states and alpha is also there, then it will not show the correct true picture. That's why we'll create one less dummy for all entities.
Actually, it will not not show error. It actually, the regression will not run. I mean, the analysis will not run. Why? Because then there will be a perfect loop. There will be a linear relationship. So because of that, the what is going to happen if you will have dummies for all the cases? What is going to happen to your degrees of freedom, and how will your matrix look like?
Yes, ma'am. Now I.
So your matrix will become such that it will be a complete loop. So when you will do that analysis, it will be a loop. Yeah. Yes, someone said something. Yeah. So fine. Now we have seen this, that how do we do the estimation when we are applying the least square dummy variable estimation. All right. Now we also, so these were the fixed effect, and in the last session we also did see the estimation where we were implying with the policy when we want to analyze the policy. So that is the policy analysis with pooled data. So yes, please.
Ma'am, before moving ahead, I want to ask a question that in first difference FPM model, we will deduct the values of 2002 from 2001, na? Previous year value deducted from the current year, or sorry, successive year values.
Yeah, successive year.
Okay. Thank you.
No, I didn't understand your question.
Ma'am, like the example you have taken, this MP, UP and Orissa, can you just demonstrate this first difference method on this example?
Oh, okay. So here what we are going to do, see, in case of within group, what we did, we did the, say for this X, for all these YIs. Okay, from these YIs, we estimated a mean, all right, for YIs. So we got a mean of YI. And what we did, we were differentiating the YIT minus the mean value. So this is going to give us the demeaned values. Okay. Whereas in case of first difference, what we are going to do, we are going to see the deviation from the successive values of the variable. All right. Now, then here what we will do, here we are seeing the deviation from the mean. Now we want to see deviation from the successive value. All right. So from whatever is the data from 2002, we will minus from the data which is there from year 1. Is that clear?
Okay.
Okay, yeah, okay. So here it will be 2, here it will be 1. Is this the confusion?
Yes, ma'am.
Yeah, even why we, I know why you are assuming that. You are assuming that these y's are increasing. That is why you are saying that it should, otherwise it should not, it need not necessarily, it can be YIT 1 minus YIT
Okay,
2.
ma'am.
It would depend, it is not necessary, but we can do this also. And we, our only thing is our interpretation would then be written in carefully for whichever way we are adopting.
Yes,
Okay.
thank
Yeah. So, yeah. So then what we were doing was, we were talking about, we have already done this. So what we were, is about policy analysis. Only thing that I did not explain here was that how are we going to do the policy analysis, and that will be done through the method of difference in difference. Right? I did mention this, but I don't remember if I have explained it completely. So, and you remember here I had said that what we are going to do is we are going to simply compare the change in the outcome across the treatment group and the control group. All right. So in order to do this estimation, what we do is we are going to have, say, for example, this is our equation, YIT is equal to alpha. Yeah, and in case of this difference in difference with policy analysis, what we want to do is we know that there will be two situations. One is where the policy has been implemented and where the policy has not been implemented. So in that case, how we are going to write? So alpha naught plus, so I'm writing here delta. Delta naught is for the coefficient, which is for dummy 2, plus say beta 1, because this is for a explanatory variable here, dt. That is why I've written beta, and say delta 1 d2 dt. All right, plus mu. Now here in this, how are we going to analyze this? What are the terms noting here? See, this is the estimator. Here, D2. D2 is the dummy, which is going to represent post-policy change. All right. What it means is that after the implementation of the policy, all right. So we are going to analyze before policy implementation, impact on treatment and control group. After policy implementation, impact on treatment and control group. So that is the experimental design. Now here, what is DT? DT is the dummy for treatment group. All right, because our main objective is to see that what is the impact of policy where it has been deployed. All right, and this D2, that is capital D2 with small d capital T, this is the interaction term. All right. Similarly, you know that in this LSDV method also, here in this LSDV method also, we can introduce the interaction terms, which is like D2x. So there will be beta 1, 2, 3, 4. So for example, it will be beta 4 D2x. We can also have beta 5 D3x. So these are interaction terms. Now, what do these interaction terms show? These interaction terms are particularly important to see the impact on the slope, right? until we have not introduced this in our analysis here because we have been focusing until now only on one component, that is alpha intercept. All right. When if we want to also analyze the impact of slope on different due to different entities, we create the interaction effects with those explanatory variables, the dummy variables with explanatory variable. Is this clear?
No, can you take this? Take this.
All right. So I request all of you to please keep yourself on mute. Yeah. So when we are doing this, how are we going to do the estimation here? The estimation will be again like the difference in difference. So we will have estimator will be, say, delta 1 hat is equal to y2 bar minus y2 bar. Here, this is for different time. So suppose that this is sometime r and this is sometime c. This minus y bar, y1 bar minus y1 bar. This is for sometime r, sorry, c. This is comma here. There is not, I don't want to take this to another page. That is why I'm writing it here. Is this clear? So this is known as difference in difference estimation, estimator, and this difference in difference estimation can be used for policy analysis. All right. Now, so the other thing which we have already discussed was about the same thing. Instead of policy, we can also do a 2-period panel data, which will be like same as what we have done just now in case of policy. This thing. So this, in case of 2-period fixed effect model, we can also create what is known as the composite error. Now, this composite error is utilized in case of random effect model. So we are now moving from fixed effect to random effect. All right. Random effect model is also known as, so until now you remember in our pooled estimation and also in our fixed effect model, what we were talking about was we were addressing alpha, all right? And in that we were, we left at the point where we had that assumption that the xis are not correlated, right? So we had to move on where the ai, the constant term or the intercept term is not correlated with. So what do we do in that case? Oh, okay, I missed one more thing. Fine, so let's start with the random effect model. This is also known as unobserved effects model. We'll see why do we do that. Okay. Now we again go back to our same equation where we have y is yit is equal to beta 1 xi t alpha plus beta xit beta k xit plus, this is our original model. Now here you know that the alpha I, all right. Now this what it means is that the AIs have mean 0. Now when we are using the fixed effect, and in that also we did fixed effect and the first differencing, okay. So in fixed effect or first differencing method, what our target was that we kind of eliminate the alpha. And because we were, you remember where we left our discussion was that this alpha is correlated to explanatory variables. All right. Now, but suppose that it is not correlated. Okay. So basically in the fixed effect and first differencing model, what we were doing was that the correlation between alpha i's and x i's is not equal to 0, and in REM we have alpha i's and x i's are correlated. All right. What it would also mean, or we can write, is that
not correlated, ma'am.
Yeah.
Alpha and xi is not correlated.
Ma'am, in both the cases you have written not equal to 0.
Okay. No, by me. Okay. Sorry. So then in case of random effect model, what does this mean is that the covariance of xi t alpha I is equal to 0 for all the t's running from 1 to t and like that. Now, what we want to do, how are we going to address it? So what we do is we define, when we have this situation, we create a term which is also known as composite error term. Okay. Now, some of the books and some of the authors might have also simplified this understanding in two ways. One is, see, when we are using fixed effect model, you know, our focus was on alpha I, where we were saying that, so this alpha I was time constant, and what it means is that in our same example of Madhya Pradesh, Uttar Pradesh and Orissa, what it meant was that this alpha I is going to capture the characteristics which are particular to this entity, particular to this entity, particular to this entity. All right. And what it meant was that this alpha I should be drawn from a value or from the analysis where you can say that you have complete information on those variables about these entities. Okay, so that means you in your model you are including more observed things. Okay, whereas oftentimes what happens is, if suppose you are going to draw, say in this case what is happening, your state is that complete state is your entity. Now if suppose instead of that complete state being your entity, if you have to choose from several units, right? If you have to choose from several units, you will be drawing a sample which is considered to be a random sample from that big population. Okay. In this case, what is happening? It is likely that you know most of the things, almost all, most of the things about that particular entity. All right. Whereas when you are going to say do analysis of some other kind, where the number of units are many. For example, if you are going to draw a sample of pharmaceutical units in these states. Okay. So suppose that output of pharmaceutical units in these states is your dependent variable. Then what is going to happen? Then you will be you will be drawing samples of pharmaceutical firms from these states, which will be only a part of that complete industry of that state. If suppose you include in your Madhya Pradesh, suppose the same, if suppose we are doing the same analysis also, if we include complete pharma industry of Madhya Pradesh, then if suppose we are including almost all units, and here also, then it will be easier to say that for each unit, we will be able to see that what is the alpha I, because we know that we have information for each unit. We have that complete line of data for each unit. Whereas suppose that it is not possible. If suppose there are only 20, 10, 15. If suppose there are only these many units, it might be possible that you can have complete data. Suppose that instead of this, there are 200, 100, 150 units. And suppose it is not possible. Then what you would do, you would draw a random sample from there. Okay, for example, here you draw 20 units, or you draw 10 units, you draw 15 units. Now what is going to happen? For these 20 units, or this entire total size of the panel will be 45 units. So for these 45 units, what is going to happen? For these 45 units, you will have data like YI, this. And that is going to give you an alpha I. Okay. Now that alpha I will be for the representative terms which are representative firms which are there here, randomly chosen representative firms. This is why it is also known as the random effects model. Whereas in this case, it is this alpha I corresponds to that particular ith firm or ith unit. Here, this alpha I corresponds to only that drawn unit. It need not be the same for entire industry. All right. So, I'm sorry, I deviated a little bit there. So why we were talking about this was that in case of random effects model, then what we do is we define a composite error term. That composite error term is given as VIT is equal to mu IT plus AI or alpha I. All right. Hence, our model can be rewritten as YIT is equal to, sorry, XIT plus, yeah, here what we will have composite term. Now, why do you think we are able to do a composite term here, and why not in a fixed effect model?
Ma'am, because their alpha I shows the represents the about all entities. Here we are not able to because the data is large and diverse. So the whatever thing is left will be covered by this composite term, error term.
Yes, and also another thing is that here you can see that there is some correlation. The second reason is that there is correlation between alpha I and Xi's. So because what we are showing in fixed effect model, the assumption is that there is a possibility of correlation between alpha I's and Xi's. So so that whereas in case of random effect model, we are assuming that there is no correlation. So when there is no correlation, we are sure that with this creation of composite error, we are not going to merge the impacts of explanatory variables also in the composite error. If we would do the same thing in fixed effect, then we will be losing on because we know that there is correlation between Xi and the intercept terms. Then we will be putting all of those in this basket, and we will not be able to see that it could also be due to correlation with the explanatory variables. Is that clear?
Yes.
Yeah. Now, so now our model has become like this. So yes, please.
Ma'am, I have a question. In this composite error term, you have included the whole intercept term, right?
Yes.
Alpha I.
Yes. Yes.
So don't we just include the error component of the intercept term?
Yeah, we are going to do that. We will talk about that. So
Okay.
right. So when you were saying no that okay, let me just clarify that here itself. See, when we started our discussion at that time, you remember that we were talking about alpha, and now in case of a random effect, what is happening is that we are having our sample or our regression is based on the sample that is drawn from the industry and which is representative sample. Now here, what is going to happen is that I'm writing it here. Now, we know that alpha is not constant, okay? But it is time constant, but it is not constant for the entire industry. So what we do is, one option is that we do the average of the alpha. Okay. Now here the thing is that since the sample is random, okay. Now what we are going to do is first we will do an average of the alpha, and if in your error term, now what is going to happen in your error term? In your error term, there will be two components, all right? One is, I'm representing it here as epsilon t and say maybe et, all right? Now this component is going to be the particular firm, all right? That is the ith firm. ith firms intercept. Okay, ith firms intercept component which has gone in the error term plus this average alpha. This is going to give us the alpha for that particular ith term, all right, with also time. Whereas this ET is the remaining error term. All right. So this component, there is a component in the error term. In the error term, there is a component which is the which is not random for everyone. This is for that particular firm, ith firm, which is representing, which is in your data. Okay. So what was happening here in this same case here, we can see. See, in this case, what we are doing, in case of fixed effect model, when we are saying that we are able to have the complete data set. So what would this mean? If you have 20 units in, or say to simplify it, we don't want to keep different sizes here. So we can keep 20 in all. Now, if this is the case, then what is going to happen? Your Madhya Pradesh, there will be one MP1, which is your first unit in the first firm in Madhya Pradesh. Then MP2, this is your second firm. Like that, there will be MP3, like that up to 20. Okay. And for each, there will be, say, 3 time periods, T1, T2, T3. That will be your data. Similarly for Uttar Pradesh also. Now, when you are estimating in your fixed effect model, the alpha I corresponds to, so if suppose we have this alpha I, which is for MP1, right? So that will correspond to that particular firm completely, right? And that is why it will be able to give, it will be kind of giving us for the entire state. Whereas in case of random effect model, we cannot say that because that alpha I is only going, we want to know it only for the, if we want to know it only for that ith firm, then what we are going to do, alpha I, first we will do an average. So what is this average? This average is for entire industry. Okay. Plus the time variant component. Here we are not going to have time variant component. Here we are including that time variant component. Is that clear? What do we want to do? Why are we combine?
Yes, ma'am. Yes, it's clear.
Yeah. See, why we are combining this is, yeah. So you can see here why we are combining these two terms. Because our main idea is to bring in the time component also. All right. And also we know that the intercept terms are not correlated to the explanatory terms. That is why it makes it easier for us. Now, with this, and also then what we can do is we can solve this equation with the generalized least square method. And we can use generalized least square method if we have large n and relatively small t. What does this mean? You know that you might have done this in your, no, maybe you have not done because panel has not been discussed earlier. So there are two definitions in all basic econometrics understanding. One is called long panel and the other is called short panel. All right. Now, what is long panel? Long panel is when you have the number of eyes, the ith, or the number of eyes or the number of units or entities. Number of units or number of entities is smaller than the number of time periods for which we have data for each entity. Is this clear? So what will happen is basically when you will see your data will look more like this, which will have here T1, T2, T3, T4, and suppose that your entity, say suppose this is up to T20 and you have only the number of units that you are collecting the data for is 8 units. This is called long panel. What is short panel? Short panel is when your number of entities or cases is greater than the number of time periods. Okay. So what we want to say here is when your panel is having large number of entities, then you can apply the GLS. All right. Now, in case of random effect model, what we are basically doing is we are introducing this term composite error term. And when we are introducing composite error term, and then when we do the estimation, what we do? So now to do the estimation, what we are going to do is we can do the differencing of the unobserved data. All right. So to see the random effect model, which is also known as the unobserved this thing. So what we do is we do the difference, that is delta yi is equal to, we continue with our beta delta xi, all right, plus delta y plus the intercept. Okay. Now here, what we want to see here is that in this equation, we know that there is no correlation between x size and the error term. All right. Now, but another thing is that there should be some variation across the eyes. You remember in our fixed effect model, what we were saying, that there should be some difference. There should be some difference in the values of xi's over time. You remember this? That means there should be enough difference between the values of xi's from of one time period to another time period. Whereas here what we are saying is that there should be some variation in the values of xi's across cases or across entities. All right. So then what we are going to do is here, this estimation, this is based on, how do we do that? YIT minus, yeah, I'm going to introduce one more term here, theta YI bar. This is the differencing method that we are going to do, which is going to give us random effects transformation. So you remember in the fixed effect models, what we were doing was, one was we were seeing the deviation from the mean, right? The other one was we were doing the deviation from the successive values, right? Now what we are going to do here is we are going to difference, we are going to subtract from a fraction of the time average of that variable. So how do we do that? So here, what is this yi? Yi is the average, where what you have done basically, if you have to estimate only yi bar is summation of values of all yi's divided by the number of time periods. So basically this yi now is the time demeaned value of that particular variable. Now here we are going to take a fraction of the time demeaned value of that particular variable. All right, is equal to, now here your alpha will be 1 minus theta, which is that particular fraction, plus beta plus, multiplied by x it minus theta, x bar I plus dot, you will have at the end beta, your composite error term, which will be VIT minus theta V bar I. So what we are doing here in the differencing, in our fixed effect models, we had in the first case, which was within group estimation, we did the time demeaning of this component. Okay. In the second one, what we did, we took successive values. Here, what we are doing two things. One is we are making the error term composite, all right. And second is we are taking a fraction, difference from a fraction of the mean. Why we are doing that? Can anyone tell me? Am I audible?
Yes, ma'am, you're clearly audible.
Okay. So see what we did in case of fixed effect model, what we did in the first step, that is within group, we did differencing with y bar, that is time demeaning. Okay. In the second, which is the first difference method, fixed effect model, in that we did difference from successive values of that variable. All right. Then we did the LSDV, that was least square dummy variable model. Then in case of random effect model, we are doing two things. One is we made composite error term. The error term was made composite. And why did we make the error term composite? Because we know that the xi's are not correlated with the
Error term.
alpha. No, not error term, alpha. The
Xi and ui is not correlated, no, in case of random effect model.
no. What is not correlated in random effect model? You have confused me now. Yeah. We started with the, we have to see that there is no correlation between
Xi and u, error term.
Between xi and alpha.
xi and alpha. So between x, in the case of fixed effect model, I think I wrote that in the previous board, that correlation between alpha and xi's is not equal to 0. That means there is correlation. This is for fixed effect. When our model can assume that alpha I is not related to xi's. This is not y, this is xi's. So we can use REM. Okay. Now, so based on this, we did one thing, that is creation of composite error, because we know that xi's are not related to alpha i's. So what we did basically, we merged alpha I with the error terms. Okay. We created composite error. That is one thing. Second thing is, instead of differencing with the average or the successive values, I request everyone to please mute yourself. There is some sound.
Participants, kindly keep yourself muted.
Here we are doing third thing, that is we are differencing with a fraction of time demeaned value of the variable. This is why we are doing the fraction. That was the question. Why we are doing the fraction is because now, oh sorry, why did I write alpha here?
Ma'am, I'm little bit confused.
Yes, please.
Here you written that the correlation of alpha and xi, that means there is no correlation, and you just written fixed effect model. But
No,
in
not
case of
in correlation there is FEM. When there is correlation, there is FEM.
there is correlation, then FEM, and there is no correlation, then REM.
Yes.
So you, oh, 0 not equal. Okay, yes.
So now what we are doing is basically, now since we have, or simple answer was that since we have created this composite error term, because of that Now we are going to take the difference with only a fraction of the time domain value. All right. Because now what we are doing is we are introducing time component even to the error term, which is the composite error term, where we have also included the component of alpha. All right. So another thing that we want to do here is talk about here is that how do we estimate what is the value of the theta. Now this, I understand that you might not be aware of the why we are introducing theta, which is a fraction of, and how do we decide that what would be the size of this fraction is 1 minus sigma mu square by sigma mu square plus t sigma a square and under root of this. All right. Now, why we are doing this? Because this fraction depends on the variance, all right, which is the variance in the error term, variance of the intercept term, and also the number of time periods. All right. Now what we do is after doing this, we estimate our model with simple.
Preeti ma'am, sorry to
Yes,
interrupt. We
yeah.
have a question in the chat from a participant. He's asking, ma'am, is there any series of hierarchical steps that we can follow when setting the model and choosing the type of model?
Type of model, or amongst the panel only, or complete thing?
The question is, we can follow when setting the model and choosing the type of model.
Yeah, I will summarize this entire thing before we go for doing the exercise in Stata and
the question
and
is
EVs.
REM and FEM amongst them.
Okay.
REM and FEM amongst them.
Okay, then it is okay. Before closing this session, I will summarize that, because that is what is going to be, done in your practice session in the afternoon. Okay, so I'm just going to, this is almost the last step here. So after estimating the quantum of theta, value of theta, then we are going to apply the simply GLS on this model, and this is what is going to conclude. This is how I'm concluding this, and we also need to know here that theta will range between 0 and 1, and the other thing is that if theta is equal to 0, all right, then basically what you are getting is kind of pooled OLS. And if theta is equal to 1, then what you basically get is fixed effect model. And if this theta ranges between 0 and 1, then what you get is your REM. All right. Now, yes. Okay. Assumptions, in case last step was assumptions of random model. So we are, it is going to be the, I mean, all the steps are the same here. So I don't know whether I should, do we have time, or?
Ma'am, we have planned that we'll have a lunch break of 1 hour from 1:30 to 2:30. And after 2:30, okay, then the next practice session will start. But however, ma'am, if you want to continue, like how long?
Maybe 5 or 10 minutes.
Yes,
more?
yes, ma'am, please go ahead. Yes,
Okay.
yes, ma'am.
Okay. All right. So the assumptions would be the same, that here also we are doing the assumptions that we have the sample is chosen from random pool of cross sections. We also know that the expected value of the error terms with respect to conditional upon the xi's and the alpha i's is equal to 0. We also know that the variance of the error term conditional upon xi's and alpha i's is constant, which is equal to variance of the error term with respect to time and case and or entity components. So this is constant equal to sigma mu square. Then the other one is that the covariance between error terms mu it for different time periods conditional upon xi's and alpha i's is equal to 0. And yes, the additional thing that is here is that the expected value of alpha I conditional upon xi is equal to the component which I wrote beta naught. All right, this is the difference in the assumption in REM, and the variance of alpha I conditional upon xi is sigma alpha square. These two things are different compared to the assumptions which we have done in the first differencing as well as fixed effect model. All right. So finally, I think I can conclude it here. Only thing that I would want to add is that there was that question that I should summarize it so that you can easily relate it with the practical exercise which will be done in the afternoon. All right. So what we do is, this is based on what we have already discussed. Number one thing is, we know that if the component alpha, which is also the component of heterogeneity, which is also known as the component which is going to show us that how the entities are different enough, all right, are different enough, and that alpha has two components. One is the time variant, heterogeneity is time variant, and the heterogeneity which is time constant. So in case of, we have seen that how we have done the analysis in the pooled OLS as well as in the fixed effect model, where we have, and first differencing within group all LSDV, where in all those places we are considering alpha to be time constant. That is why we are denoting everywhere alpha I. There is no T subscript there. All right. Now, so first step in understanding your analysis is, you can do a pooled OLS. You know, when you can do a pooled OLS, you know the difference. Now we have already discussed the difference between the pooled cross section and the panel data. Okay. Then the second step is, if you see that that may not be the, how do we see that whether your alpha, the component which is of component of heterogeneity or representing heterogeneity, whether that is different or same. So you remember we started with that alpha is same or constant. All right. So to see whether that is same or not, what we do is there is a test which is called Bruch-Pagan test. In the Bruch-Pagan test, we start with the hypothesis. Our null hypothesis is that alpha is constant. What it means is that there is no effect of time and entity. So alpha is, it is alpha I only. So there is no effect of time. It is time invariant. In that case, what we do is we see that if the p-value that comes out after running this test is greater than 0.05, then we accept the H0, which is null hypothesis. What it means is that our analysis is good enough to be done with pooled OLS estimation. Okay. If P is less than 0.05, then what we do? Okay. Then although in our theory, in the theory which we have understood, in that we went on from pooled estimation to fixed effect and then to random effect, because theoretically it is easier to understand that way. But in practice, what we do is after doing this Bruch-Pagan test, we are able to say that when H0 is, so what it means is we reject H0. After this test, when we are rejecting H0, we don't go for FEM, but we go for REM. So we do random effect model. And we undertake Hausman test. Hausman test will have, while conducting that, the hypothesis will be that that the random effect model is preferred. This is our null hypothesis. Okay. And if we get a p-value which is greater than 0.05, then we accept the null hypothesis, which means REM is good for our analysis. But if p-value is less than 0.05, then what we do is we reject null hypothesis. What it means is that REM or the random effect model is not a preferred model. So then what you do? Sorry.
Ma'am, I have here a little confusion. If p-value is less than 0.05, then we accept the null hypothesis, or greater than 0.05?
Less than.
No, we are, if P is greater than 0.05.
Then null hypothesis will be rejected now.
No, what do we?
Then we accept the null hypothesis if it is greater.
Yeah.
Okay.
What you are getting confused is mainly because in most of your classes, and that is what we all do, is we formulate the alternative hypothesis.
Yeah.
That is why you are getting confused. Here we are formulating null hypothesis. Yeah. Is that clear now?
Okay.
Yes.
Yeah. So if this is the situation, then we go for fixed effect model. Okay. So that's all from my side.
So Preeti ma'am, shall we take a lunch break for an hour and resume our class at 2:30?
Okay. And I would also like to share that Dr. Shubhendu Pradhan, in the last sessions also, he did that. So Dr. Shubhendu Pradhan is going to take the practical session on using STATA and he will also demonstrate the conducting of fixed effect model and random effect model on Stata.
Preeti ma'am, would you like to share
also-
any data so that I can pass it on to the participants and they can already have the data in their Stata software so that they can apply?
Yes.
Would that be a good idea?
Yeah.
So ma'am, you can email it to me. I'll email it to the participants.
Okay, fine. I'll do that.
Yeah, sounds good. So dear participants, we'll resume at 2:30 and you can stay logged into this meeting and we'll come back at 2:30. Thank you so much, Preeti ma'am. You'll come back, right? After
Yeah,
Dr.
I'll be
Khan?
here only. Only thing